Hi and welcome to this quick video. My name is Greg and we're going to be talking about accelerating software applications with CacheQ Systems Thread Parallel Compiler. Just as a quick overview of what we're going to talk about today, I'm going to give you a little background on why writing high-performance software is challenging. I'm going to introduce and give you an overview of CacheQ Systems compiler collection, which is called QCC. I'm going to do a quick demo, and then I'll leave you with some links or where to go for more information. Generally, a software developer spends most of their initial time working to make a piece of software function correctly, and then they turn after the fact to trying to make it work faster. And also, most of the algorithm developers or software developers in general don't fully understand the very low level details of the hardware on which they're running, and therefore it makes it challenging for them to get very high performance code. They're relying upon compilers, which do a fantastic job, but generally speaking they only target one core and one thread, and can only do so much without some help and guidance from the software developer. And they're specific to a single target. So in order to make code run fast, you first need to understand that the code as written in your editor is essentially sequential in nature. And usually it has loops in it. And loops, if you have a block of code which has a number of instructions, we'll say C number of instructions, and you iterate across these loops n times, your wall clock time is essentially n times C. If you want to run faster, generally speaking, you're going to be turning on aggressive compiler optimizations such as the GCC-O. The default is 0. You can turn this parameter up to 1, 2, 3 or fast, and it enables more advanced optimizations such as loop and rolling, even to the point of turning on some non-standard math optimizations. And it's up to the developer to ensure that their code is still functioning correctly. But it's still limited to superscalar execution on a CPU, even high-frequency CPU. To get beyond that and to run even faster, you have to begin to explore how to run things in parallel. And in particular, running things in parallel requires redundant hardware resources on which to run. And the theoretical best that you can do would be to fully unroll a loop and have fully redundant hardware and implement it in a pipeline. And if you do that, you can get your execution time to n plus C instead of n times C. The trick there is if you have loop carry dependencies, when you have a piece of data inside a loop that's dependent upon a memory location either outside of the loop or updated in a different iteration of a loop. So this becomes very quick, very difficult very quickly. So writing for parallel code is not easy. And I'll say a few more things about this. There's generally kind of a couple of types of parallelism, and I'll loosely define them as the first one would be coarse-grained parallelism. And this is typically where you have multiple executables running on separate CPUs, and they basically are required to operate on independent data sets, and there's not a lot of coordination or communication between these parallel executables. Again, this requires the user to pretty much architect their code and rewrite it in a special way using special APIs such as MPI. MPI stands for Message Passing Infrastructure, which works on a distributed memory model, or other tools like MapReduce with Hadoop. The other type of parallelism is fine-grained parallelism, where you have basically multiple threads running on a single CPU, generally operating on a single data set, and there's a lot more coordination between the threads. And usually the solution there is another API called OpenMP, which works on a shared memory model, or you can pretty much roll your own with pthreads or some other sort of threading library. But again, it's pretty much up to the developer to understand this technology, to understand the hardware that they're running on, and it's not easy. So this is where CacheQ's compiler, QCC, really comes into play. QCC is able to target this fine-grained parallelism in a manner in which the software developer really would have a very difficult time doing on their own. It can also work with MPI or coarse-grained parallel platform if you would like, but really extracting a lot more parallelism out of your code is where the benefit comes from. And that's our system. It's our multi-core compiler platform with CacheQ. What we do is we take single-threaded code and we generate multi-threaded executables. And lots of software developers really struggle with this because it's a very complex task. Our compiler performs extensive code analysis and optimization to achieve automatic results that are on par with what you can get manually coding for OpenMP and MPI. And it's a very software-centric verification and optimization environment. It's very familiar to people that use and understand compilers such as GCC. We have a complete development platform which includes the compiler as well as other tools that are necessary for understanding your performance bottlenecks and getting better results, such as performance estimation, resource estimation, profiling to understand which portions of your code are executing the most, and partitioning, which is the assignment of blocks of code to one resource or another, or in other words, scheduling the code to be executed on different types of hardware resources. We support heterogeneous platforms, and that means the application can execute across a broad suite of devices from a single compiler and in a single system. This includes multi-core x86, so an Intel or AMD x86 processor with multiple cores, with or without hyperthreading, which can support multiple threads per core. We also support multiple ARM cores, multiple RISC-V processors in the same system, as well as extending even further and more advanced heterogeneous systems, such as systems that include an x86 processor with an FPGA attached to it via PCI Express bus, or an ARM bus like the Zinc devices, or microchip PolarFire SoC. So our methodology is essentially the compiler will focus on the loops in your design. So anything not in a loop is typically not interesting because it'll essentially run very quickly through the tools. And furthermore, most things are not only in loops, but they're in nested loops. So the tool will essentially try to thread the outermost loop, and then it'll leave the innermost loop to build a custom data flow pipeline, which is already highly parallelized. We do extensive pointer analysis, and this is really required so that the tool can understand which threads might interfere with each other. And the compiler also really understands the processor architecture and its limitations, so it'll only thread loops if there aren't things like contention for cache line accesses. It'll also interleave writes among different threads, which also improve performance. And it'll restructure the code that's generated in order to increase the likelihood of success. It recognizes things like summation, strength reduction, and much, much more. So this gets particularly complex when you're doing floating point math inside of loops. And the goals for multi-threading generally are to deliver high performance with an easy-to-use compiler that has very limited impact on the software developer. They don't have to really know the hardware that they're targeting. They don't really have to rewrite or use special APIs, and they don't have to write pragmas into their code to tell the compilers how to parallelize blocks of code. The one trick or caveat there is that we do require, or actually we don't require, but sometimes it is very helpful to use a C construct, which is the restrict keyword. That's occasionally required, and that basically tells the tool that you will only access a given area of memory through this pointer, and that really simplifies and improves the optimizations that we can perform safely. The tool will detect when cache line movement is going to be an issue and schedule operations to optimize those loop accesses, and it'll avoid threading short loops when the communication overhead might negate the benefit. In addition to that, we provide information on the implementation details to the software developer. This includes reporting about which loops can be threaded, as well as giving you other important information about how to best optimize your runtime. And again, it's going to fit into existing workflows because, first of all, you can develop hybrid flows where you can call, you're not required to use our compiler for all of your code. You can use C++ for a high-level portion of your design, and then call into a function, a C function, which is optimized using the CacheQ compiler. We can work with OpenMP or MPI. They are not required in order to get high levels of parallelism out of our tools. And you can also use your final compiler of choice, GPP or Clang or ICC, with the code that we generate quite easily. And then above all else, we won't break working code. And this can be tricky if you're accustomed to trying to optimize floating point operations with a tool like OpenMP, or with things that may require, for example, random number generators, which are not thread safe. If you're not used to understanding this, you can just turn on OpenMP pragmas. That's easy enough, but you can get the different results and even incorrect results. So it's not as easy as it seems by just turning on OpenMP. You actually do have to spend quite a lot of time to optimize and rewrite your code just for targeting those APIs. So I'm going to jump to a demo here and show you what we are talking about. I've chosen an algorithm called Black-Scholes, which is basically a simulation of human behavior doing options trading. And I'm going to show you calling the Black-Scholes algorithm with 20,000 options. And I'm also going to demonstrate compiling for both Intel x86 as well as Apple M1 Silicon, and we're going to come back and compare the results in just a moment. Here we have on this left window here the C code for our Black-Scholes algorithm, and I just wanted to show you this line by line to demonstrate that it pretty much has everything you expect out of C code. It has pointers, structures, functions. Pretty much the entire program is passed into the QCC compiler. The critical stuff happens inside this BS loop, but we may not know that yet. It has some argument processing. It has a calyx in there, and pretty much a pretty standard C code without any special APIs, no pragmas involved here. So I'm going to exit out of that, and I'm going to open up my run script here just to demonstrate how we are going to compile this. And the first thing I'm going to do is pretty much compile it with and run it with GCC, just to show you that the code that we're running executes. And I just ran it on 100 stocks, which is just a good starting point here. And pretty much this is the simulation that compiles and runs. The expectation is before you go into QCC, into the CacheQ tools, that it compiles and runs with GCC and it passes Valgrind, basically to check for memory leaks and that sort of thing. In order to run it through the CacheQ tools, I'm going to call QCC with the same optimization levels that I did with GCC, which is -03 here. And I'm going to tell it what my output file name is, the exact same source file, and going to compile it. And that runs pretty quickly, same level, basically the same amount of time to compile as GCC. And then we have a command called CacheQ run, which will take the database that's generated, which is a .cq file, and it runs this runs that executable in the same way that you call the executable directly. And I'm going to call the time command, and I'm going to run that on the same args that I ran. Actually, I'm going to run it on a much larger number of args. I'm going to run it on 20,000, which is what I had defined up here. The compile ran, And by default, without any other options passed to the runtime, it'll by default run on 2 threads. And you can see that the actual final user runtime was about 3.6 seconds to run on 2 cores with 20,000 stocks. So I'm going to go back to my GCC executable here, and I'm going to measure the exact same arguments. So that was 20,000 stocks. I'm going to go back and call my GCC executable. So I'm calling the time command, and I'm just formatting the output. And I'm putting the time measurement into a text file called runtime.txt so we can measure the result. But essentially, I'm just calling the GCC executable with the args, which is 20,000 stocks. And you can see from the actual program output, it took about 3,600 milliseconds, or about 3.6 seconds. And then I'm going to iterate through the number of threads. And the number of threads is a runtime option to CQ run. So when I run CQ run, I call it with -v, which prints out some additional information like verbose. And then I give it the -mt switch with a number, and I can give it a number between 1 and the maximum number of threads on my core, and we'll see that we print out how many logical cores are available to you. And essentially, I'm just going to iterate through that in a for loop, and I'm going to run it 12 times, and then I'm going to measure the runtime from each of them and put that into a file called runtime.txt. So don't let this time command thing really confuse you. All I'm doing is just measuring the actual runtime. And so it ran all 12 times, and I'm going to open up my text file here and show you what the runtime is, right? So the GCC runtime was 3.6 seconds. It took 5.9 meg of memory, and it passed because it didn't have a 0 return code. So as we can see, with one thread, QCC took, GCC took one thread and ran in 3.7 seconds. One thread with QCC also ran in 3.67 seconds. But we can pretty much see a pattern here that if we scale up to 12 threads, that entire program ran in 0.6 seconds. So that's a pretty significant speed up, which is pretty cool. I'm going to jump back to another machine here, and I've got the same experiment loaded on my Apple M1 device here, running an ARM-based M1 Apple Silicon device. And I'm going to run the exact same experiment, right? Same piece of code. I have some setup stuff here, but essentially I'm just going to iterate through the same thing, calling GCC and measuring the runtime, and then I'm going to iterate through the maximum number of threads, which on the Apple M1 Silicon happens to be 8, because there's 8 cores on this device. So I'm going to stop at 8, but I'm basically going to run 8 different experiments and measure the runtime on all 8 of those as well. So I'm compiling with GCC to measure that, and then I'm compiling once with multi-threading turn on for CacheQ, and then I'm going to run it. The same arguments with differing numbers of threads 8 times. So you can see I was running with 6 threads, running with 7 threads, running with 8 threads, right? And then the end result is runtime.txt, right? The Apple M1 Silicon is pretty impressive, right? So the native GCC running on the ARM with 20,000 stocks, same as my x86, took 1 second. So that's 300% faster. And then the runtime with scaling up to more threads and more using those 8 cores that are available to you. On 4 cores, you get 290 milliseconds, so 0.29. Going all the way down, if you use all 8 cores, it's 0.26 seconds. So this is an Intel x86 Linux machine running Ubuntu, I think 18.04. It's got 16 gig of RAM, And it's got 6 physical cores with hyperthreading, so that's 12 logical cores. So with 12 cores and 20,000 stocks, exact same code, I was running in 610 milliseconds. The same piece of code running on Apple Silicon with only 8 gig of RAM and 8 cores. Ran the same piece of code in 260 picoseconds. So that's, I'm sorry, not picoseconds, 260 milliseconds. So that's pretty impressive. I'm going to jump back to my desktop here, and I've actually plotted these results, and I'm going to show you a graph of what that looks like. So we saw the compile times for both the x86 and the Apple M1. I'll just summarize the runtime. It was pretty impressive. The speed up of the x86 was about 486% on using 6 threads compared to single thread GCC. And the speed up on the Apple M1 was about 400% using 7 of the 8 cores on the ARM devices on the M1. And I plotted the run results, comparing each of them to each other based on the number of threads. So on the left here is GCC. The beige is the x86 numbers, and the black are the Apple M1 numbers. And you can see even just on GCC that the Apple M1 is almost 4x or 3.7x faster, just comparing those two. But when you use single thread QCC and then moving toward the right, using the runtime option to increase the number of threads, the runtime gets pretty substantially faster. So I think the fastest run here was with I think 6 cores on the x86 and with 7 cores on the M1. So the speed up here is pretty impressive, and even more impressive was the fact that you didn't have to use or learn OpenMP or MPI in order to achieve it. You just use our compiler with the -MT option. So thanks for watching. If you want more information, you can find us on the web at CacheQ.com. You can also subscribe here on YouTube. We'll be issuing more videos with more details about our technology. And you can follow us on LinkedIn, or you can contact us directly by emailing at sales@CacheQ.net. Have a good day, and thanks a lot.